Hello and welcome. My name is Pawel. I'm the director of the Query Center in TDA. And today I want to tell you about some new ideas of how to bring local information into global invariants. I want to thank very much to the organizers for giving me ability to talk over here. Okay, so here's the schedule for today. We'll start by classical mapper algorithm. Then we'll move to a ball mapper, kind of motivating by certain possible problems with mapper algorithm. We'll see how to combine them and how to use new coloring functions on the top of them. Starting with mapper algorithm, what we need to have is a point cloud X. Over here, it's kind of uniformly sampled from a diamond shape. In addition to the point cloud X, we need a function from X to Rn, typically n being 1 or 2. In this case, our function assigned to a point just y coordinate of that point. Okay, so we have the function. Now we want to be able to say that f of x is close to f of y for certain x and y. We need a criteria for what it means for those two numbers to be close. And in order to have this criteria, we take an overlapping covering of the codomain of our function f. So 2 points will be considered close, or the values of 2 points over the function f are considered to be close if they end up in the same element of the cover. So what we do next is to take all the points that are close to each other, namely all the points that lives in the codomain, in the inverse image of one element of the cover, for instance all those points over here, and having this collection of points, we are running a clustering algorithm in this collection. So for this collection of points, we can assume that a reasonable clustering algorithm will tell us that there is only one cluster. Likewise, for the inverse image of this interval, which consists of this collection of points. If we take, however, the inverse image of the middle interval, we'll have those points over here as well as those points over there. And over here we can assume that a clustering algorithm will tell us that there are two clusters in the inverse image of this middle interval. Now, we want to construct a mapper graph. Every connected component that we just located will be a vertex of this mapper graph, and they correspond to each other via colors. And we'll place an edge between a couple of vertices, if and only if the corresponding clusters will have non-empty intersections. So there are 4 non-empty intersections over here that corresponds to the 4 edges in the mapper graph. And mapper graph is a working horse of TDA. It's used in hundreds, if not thousands of papers. Let me just mention the most famous paper by Gunnar Carlson and co-authors, where they consider, where they actually find a new type of the breast cancer with perfect survival. And one of the reasons why mapper is so powerful is because it has quite a few knobs to adjust. So there is the cover of the line, the lens function, which is the function f that we just consider, the clustering algorithm of our choice. And sometimes it may be not easy to choose them all in the proper way. Sometimes we may be tempted to make up some of the parameters, especially the lens function. Let me just say that thing may be dangerous, and I won't be able to show you the full construction, but the following statement is true. Think of your favorite graph G. It can be any graph you want. Then I will be able to find a point cloud X, which essentially will be a grid of points in R3, on which I will construct a function from this point cloud X into the real line, such that if we run a mapper construction on the point cloud X, and this function which I make up for you, then the mapper graph will be a G, your favorite graph, whatever it is, plus one disconnected vertex. So we need to be careful. A lot of freedom. It's also a lot of responsibility. The question is, what can we do if we don't know how to set up those parameters? Well, maybe sometimes it's better to start with an algorithm that don't have that many parameters. And my suggestion for this will be a ball mapper algorithm. Here is how it works. So let us start with a point cloud. Over here it has the shape of the letter Y. And the only parameter of the ball mapper algorithm is a positive constant epsilon. We use it to create an epsilon net on our point cloud. What is an epsilon net? Well, it is a subset of points having the following property. Every point from our point cloud is at most epsilon away from a point of the subset. In other words, if we take balls of the radius epsilon, place them at every point on the epsilon grid of our subset, then the union of those balls will cover our whole point cloud. And now what remains to do is to take a one-dimensional nerve of that cover, very much like we did with the construction of mapper, standard mapper, where we also take a one-dimensional nerve of a cover. This graph, we'll call it a ball mapper graph, tells us something about all the input point cloud. Heavy center, free flares going out of that center. It has been implemented, so if you want to play with it, you can use the R package, you can also use the Python package, and you can just go ahead and try it out. And because it's kind of simple, it don't have too many knobs to adjust. It picked up some attention with my collaborators in economics and finance. Let me just mention one application in which we looked at the UK census data, and based on them try to understand the communities who voted to the UK to leave in Brexit referendum in 2016 and those who voted to remain. Well, the people who want to leave are the people in blue. The people who want to remain are in green and yellowish. What you can see from that picture, we use essentially 20 variables from the Census Bureau, is that the community of people who wants to leave is very homogeneous. The community of people who wants to remain is much more heterogeneous. And you can do all sorts of analysis, comparing those preferences in Brexit to the preferences towards political parties, and you can draw some very nice conclusions which are described in those resources. So please feel free to take a look if you would like. Okay, so what we did so far, I introduced you the mapper algorithm, I introduced you the ball mapper algorithm with essentially one use case, which is a joint work with Simon and Wonling Rutkin. And what I still want to do is to show you how you can use the dimension and curvature based coloring function, how we can use the mapper and ball mapper as a way to visualize function from Rn into Rm, and how to build mapper on the top of ball mapper. And in order to tell these stories, let me take you to the space of knots. That's a joint work with Davide and Radmila. So, what is a knot? It's simply an embedding of S1 into R3, up to continuous deformations. So if we have two embeddings that can be continuously deformed to each other, they represent the same knot. But we have, of course, infinitely many knots. Those are complicated objects. Therefore, people introduced many ways of describing them. Some of them are not polynomials, like Alexander-Jones polynomial or HOMFLY-PT polynomial. Some of them are homology theory, like Kowanov homology theory. And in all those cases, we can select the basis of polynomials, we can select the basis for the rank of homology group, and those invariants provides us a point cloud that we can visualize and examine using the tools of topological data analysis. For instance, if we take all the Jones polynomials of all the nodes up to 15 crossings, we have roughly 250,000 points in 32-dimensional space. This is the dimension of the space we get after fixing the basis of those polynomials. And here's how the space looks like. Well, we can color them by many things, including the quantities that are of interest to the people in knot theory. For instance, the signature of the knot. What we can see from here is that, in this heavy center, there's a mess. But once we move away from the heavy center, the knots with the same signature occupy kind of very well-defined regions of the space. They do not mix over there. We can ask the same questions about the Alexander data. So here's the Alexander polynomial data for all the nodes up to 15 crossings. It's not as encouraging as Jones, it's much more linear. We may speculate that this thing is much less dimensional. We can try to see what are the signatures of those nodes. This is the plot we get. Again, it's nothing close to the clear picture we get from a Jones data. So we can speculate two things essentially, that Alexander is somewhat weaker than John's polynomial, and I will not comment on that. But we can also speculate that the space of Alexander polynomial is lower dimensional in the space of John's polynomial. And well, we can actually try to verify this hypothesis thanks to the local estimators of the dimension and curvature I'm working on currently with John Harvey. I will focus only on the local estimation of the dimension. And for that, we can use the distances to the cave nearest neighbors and the ratios of those distances. That gives us an estimator of the dimensions. Instead of distances, we can look at the angles between the nearest neighbors. That also can give us some estimation of the dimension. We can use the local PCA in order to try to reconstruct the tangent space. Again, that gives us an estimation of the dimension. Let's try to run it on the spaces we just discovered. So for the space of Alexander polynomial, we see that in most cases the dimension seems to be 2. Towards the periphery, dimensions drops to 1. However, those estimators, they may fail in certain cases, and well, here are the percentage of cases in which they fail. They fail roughly in 5% of cases where we are somewhere in the middle of the structure, and they fail essentially every time when we are in the periphery. You may say that that's a pretty bad descriptor. Let me, however, tell you that well, the polynomials we consider are integer value polynomials. So we are looking at the point clouds, which is located in the integer grid. That's a pretty, let me say, challenging point cloud for this type of algorithms. We can do the same for John's, and we see that John's is almost three-dimensional. The space of John's polynomials is almost three-dimensional, except from, again, the periphery where it becomes one-dimensional. Percentage of failure a bit higher, but still we fail every 1 out of 5 nodes in the middle, and we fail every time in the periphery. So now that's a new type of decoloring functions which are coming up in our paper with John, coming up hopefully very, very soon. Okay, but the knot data, it's a very interesting data set because we have objects which are knots and a number of very different characteristics of those spaces. And it is natural to ask the question how to compare the spaces of the descriptor. Are they similar? Are they different? Is one better than the other? And kind of a more general question along those lines is, well, once we have a function from Rn into Rm, how to visualize it? Can TDA provide us a way? Well, let's think about it. If n equals m equals 1, then we can certainly do it, and we do it from early days of our mathematical education. If we have a function from Rn, which is still a scalar value function, then we can still do it. For instance, well, the plot of the Brexit support on the top of a roughly 20-dimensional space is a perfect example of that function. And we can express this function as a coloring, as we did over here. Okay, that's possible. How about the most general situation once we have a function from Rn into Rm? Well, in that case, we can build a model of this space in the domain. Let's say this is the space of Alexander polynomial. And we can build a model of the space in the codomain. Let's say this is a Jones polynomial. The question is, well, where the points from every single ball in the domain are mapped in the codomain? Well, we do have this information because for every ball we know which knots are covered by that ball, and we can just ask the question, okay, where they are in the space of Jones polynomial. That's precisely what we can do. That's precisely what is implemented over here, and that's a nice visualization tool by my PhD student, Davide Gurnari. And what you can do over here is you can just select the points in the domain, and the software will tell you where their images are located in the codomain. So we can do it for different collections of points from the domain. That gives you an idea about the function. In that particular case, as we move from this end of the Alexander polynomial space to that end, it really corresponds to moving from this end in the Jones space to that end. And this is kind of a continuous motion. If you want to give it a try, well, here's the link to the software. And there's also a link to the more detailed explanation on how it works. Okay, so we can use TDA to visualize functions from Rn into Rm, but we can do also much more. In order to do it, well, there won't be two, there will be only one more example of exotic knot descriptor, which is the HOMFLY-PT polynomial. So this is a polynomial of degree 2. In this case, it is colored by the knot signature. It's not nice. It's not as nice as Jones polynomial. In the knot theory world, it's considered to be much more general than Jones polynomial. Well, we'll use this thing as a gadget. So here's what happens. We have this HOMFLY-PT polynomial, and this is a polynomial of two variables. We can get the Jones polynomial by substituting the first variable with t to minus 1 and the second variable with square root of t minus 1 over square root of t. And then, well, if we restrict to knots up to 15 crossings, the codomain will be something 32-dimensional. Well, that's not good enough for a conventional mapper, but what we can realize is that ball mapper is nothing more than a coverage of the codomain of that function. And therefore, we can take every ball from that coverage, look at all the points that are mapped to this ball. Well, those are the points that are closed in HOMFLY-PT, and, well, run our favorite clustering algorithm over there. In other words, cutting long story short, we can run a ball mapper, we can run a mapper algorithm on the top of ball mapper algorithm where this algebraic relation is just the lens function. And if we do so, well, this is our codomain, it's the Jones polynomial, and if we construct a mapper on the top of it, this is what we will get. And you may realize that those two graphs looks, well, kind of similar. In fact, if you look at the software, you will realize that essentially if we take an inverse image of every ball in this Jones space, there will be only one cluster on the top of it. By quite a bit of abuse of notation, I can say that the fibers of that map are topologically trivial. And this is what we get for by constructing mapper on the top of ball mapper for the projection from HOMFLY-PT into Jones. You can get a similar projection from HOMFLY-PT to Alexander using this map as the lens. This is what you get. You won't get this quote-unquote trivial fibers anymore, and all of this has certain consequences in knot theory, which I don't have time to discuss. Let me just say that this methodology of constructing mapper on the top of ball mapper is much more general than just the knot data. Imagine that you have very high dimensional data and you do some projection into high dimensional data. And by high, I don't mean R1 or R2, I mean really something higher dimensional. That's not the case where you can use the standard mapper, but you can build a ball mapper representation of this high dimensional data, use this projection as the lens function, and construct a standard mapper on the top of it. Why I think it may be beneficial? Well, the reason is that when you are projecting into high dimensional space instead of R1 or R2, there you are much less likely to lose any important information. So I hope we can recover a much better mapper type algorithm by combining those two ideas. So the take-home message, well, there are many knobs in the mapper algorithm. They're very useful, but you shouldn't put it to extremum. And that was the example with that you can get any graph you want if you put it to extremum. It may be beneficial to try methods with fewer knobs first if you don't know anything about the data. It may be useful to use some new coloration function, local dimension curvature, visualizing function from Rn to Rm. That's something we can do with mapper terminology. And we can also build mapper on the top of ball mapper in kind of a cascade. And I believe that can be very beneficial to analyze high dimensional data. Much more beneficial than using mapper, all ball mapper alone on the data set. So that's all I want to say. Thank you very much for listening. Let me just mention that in my Dioscuri Center, I'm constantly looking for good postdocs and PhD students. So if you are interested in this type of research, if you would like to work with me, please drop me a line. Also, I'm sorry I cannot be with you in person, but if you have any questions or comments about my talk, please feel free to contact me. I will be very happy to talk to you. Thank you very much. Have a good day and goodbye.